JCNS 2 Center, Jülich Center for Neutron Scattering. It is the institute that basically focus or investigate on the correlated electron materials for the sake of functionality. This is what of most interest at the end for us, because this hopefully one day will be applicable in the information technology application. Some of these functionalities have been already discovered, such as the metal insulator transition, but also the magnetocaloric, electric, multiferroics, and other functionalities. But there is a lot for you to discover. Hello everybody, I am Sabreen Hammouda. I am delighted to be here today to give you a little, or to take you on a journey toward the multiferroic materials where the ferroelectricity are driven by unconventional mechanism of charge order, basically. Yeah, so what is multiferroic material? It's the material that combine magnetism and ferroelectricity. What is this important for? It's important because you can, in this case, switch the magnetization by applying an electric field and the polarization by applying a magnetic field. And as an application, for example, in this case, because we encode the information as a binary bits by magnetization of these two blue layers here, either 1 or 0, parallel or anti-parallel, we do this remagnetization by applying current. But the current will cause two problems, however, the power consumption, but also the heat problem. In order to overcome this problem, if I insert a multiferroic layer here, then in this case, you can switch the magnetization by applying voltage or electric field. And in this case, we overcome the problems I mentioned. Why I'm focusing on this multiferroic materials that are driven by charge order? Because there was a proposal in 2005 by IKEDA that this lutetium ferrite compound, which has this basic structure, is ferroelectric. Basically, because this compound has the different valences of the iron, +2 and +3. And the arrangement of these different charges in the bilayer lead to a charge difference that are separated by the distance you see here. It's the thickness of the bilayer, and this leads to electric dipole and so polarization. Okay, for different rare earth elements, for example, the yttrium ferrite, which has a larger rare earth ion size, you can see that my previous colleague, Thomas Muller, he investigated the charge order in these materials, and he found that it's not polar, but rather charged bilayer. Okay, but for the ytterbium-1, which has basically similar or almost similar rare earth ion size to the lutetium-1, it exhibits a polar bilayer, which has an antipolar stacking, as you see here. This configuration was found by Hailey Williamson based on the single crystal X-ray diffraction she did. She see some of the superstructure reflections that you see here. This is basically the HHL plane in the reciprocal space. So these superstructure reflections you see here at 1/3 line, it comes from the charge ordering. And it is commensurate. Why it's commensurate? Because we have this superstructure reflections exactly at the 1/3 line. Okay, and what I'm doing here, basically I want to take the lutetium ferrite, as you see here. As I said, because it's similar to the ytterbium, it has antipolar stacking, and do some structural modifications, like insert this block here. In this case, I modify the relative interactions between the bilayers, and also we have a different stacking than what we have in the lutetium ferrite. Will this make the lutetium ferrite to be polar? This is what I want to investigate. Also, if I again take the lutetium ferrite but insert 2 blocks of the Lu2Fe3O7, will also this render this compound to be a polar? By the way, this compound is called the first intercalated compound, Lu2Fe3O7, and this one is the second intercalated compound, 3,4,10. Just to know that these compounds are crystallized in different symmetries, alternatively hexagonal and rhombohedral. And according to most power studies done by these people here, or according to published articles, that the iron in these single layers are Fe+3. Okay, so in order to answer this question, we grow single crystals of the Lu2Fe3O7, the first intercalated compound, by floating zone method. However, there is a problem. It's not only that the crystal structure is complex, but also we have the problem of the stoichiometry, which means that one needs to really check that you have here 7. You have the right amount of the oxygen in your sample. And how I did this? By using the flow of the carbon dioxide to carbon monoxide during the crystal growth. And of course, I don't know what is the right ratio. Therefore, it's a trial and error. You use different gas ratios, as I show here. And then we grow the crystals, we do boundary X-ray diffraction, and we check what are the obtained phases. As you can see here, I have the one I intend to grow, the Lu2Fe3O7. However, there is a new compound, it's the 3,4,10, which comes by a stacking fault. This is quite common fault to happen in the layered structures. So we get this compound for free. Okay, and now we want to assess the stoichiometry of these samples, of the crystals. The best way to do this is basically by measuring the magnetic properties and compare it with the non-intercalated compound, because it has been known previously that the lutetium ferrite stoichiometric one exhibits a sharp feature. As you see here, my crystal Lu2Fe3O7 don't really show a sharp feature, which means the magnetic correlation here are reduced. It's not as good as in the 1,2,4. But what about the 3,4,10 then? We have here a sharper feature. This is nice, but it's still not as sharp as in the non-intercalated compound. Okay, also I took these crystals, but now a large size crystals, to the reactor FRM2 to measure the polarized neutron scattering at DNS. I wanted to check, in fact, if the large crystals are exhibiting diffuse scattering or magnetic superstructure reflections. And as you see, I got diffuse scattering, which means, yeah, the samples does not really show a highly correlated magnetic scattering. We come to the interesting point here is the charge ordering, the main goal of my project. I check the crystals by doing single crystal X-ray diffraction, and I have seen that we have 3 types of charge ordering. This is just the HHL image in reciprocal space. I found that one type of the crystals exhibit 2-dimensional charge ordering. You barely see diffuse scattering here. That means the charge ordering are locally in the bilayers only. But also, we have another type of crystal that exhibit these superstructure reflections. It's zigzagged, and it's not exactly at 1/3, 1/3L, so it's incommensurate 1. This was, by the way, reported before by Yang 2010, based on powder studies. And the most interesting part is this one. We have a commensurate superstructure reflections that can be described by this propagation vector, 1/3, 1/3, 0. What does this mean, the propagation vector? It's basically how you get from a fundamental reflection to a superstructure reflections. This one is different than what found in the lutetium ferrite. There you have 3/2, not 0. Also the 3,4,10, it's the same. We have 2-dimensional, we have incommensurate, we have commensurate, and all these results are new because this is the first time there crystals of 3,4,10 exist. Okay, to give you an overview about, or a sense about the size of charge ordered regions in the compound, we did estimation for the correlation length out of plane, and it turned to be that for Lu2Fe3O7 we have short correlation length compared to the non-intercalated compound. However, for the 3,4,10 we have a much higher correlation length. We we have about 90 bilayers, which is even larger in the non-intercalated compounds. Okay, it's known that the crystal structure, without having any charge order, you have specific symmetry, but when these superstructure reflections exist because of the charge ordering, this symmetry gets distorted. We want to know what is the new structure, what are the possibilities when the compound have these charge order have superstructure reflections. So to do so, we go to software called IsoDistort. We enter the propagation vector, this one, and we do symmetry analysis. We simulate the possibilities. And here you see the all possibilities. The first one is this one. It's orthorhombic CM-CM symmetry. But this one is not possible. Why? Because it's overall charge. It's not neutral. The second one is the monoclinic one, C2/M. This one has a charge by layers. But this one is also not likely. Why? Because the distance between the different bilayers, the neighbor bilayers, are about 6 angstrom. And the charge order driven in this symmetry by the charge hopping between the neighboring bilayers. So this makes the symmetry not likely. We left with two likely symmetries, either this orthorhombic one or this one. This one, the CMC21, is polar, but in this direction, and the other one, it's antipolar. However, it's polar in this direction. And what about the 3,4,10? 3,4,10 has a unique solution that is definitely polar. Okay, now we want to do a refinement. We want to do single crystal X-ray diffraction, we want to collect the intensities, and then afterward decide what type of charge order do we have. But unfortunately, we have a problem that the superstructure reflections, when measured at supernova in-house, that they are closed. We have an overlap, and to overcome this problem, we went to the beamline P24 at Dizzy because it has, of course, a better resolution, and we collect reflections for the refinement for both the 237 and 3,4,10. And yeah, so I tried to refine the 237 crystal structure when the charge order are there, neglecting the superstructure reflections to know what happened. Before the charge, neglecting the charge order, you should have this symmetry, B63/mmc. So I said, why not refine it in P63/mmc? This is what we call the average structure. And then I have notes that this lutetium atom here, it gets elongated. And this elongation has been observed before for the non-intercalated compound as an effect of the charge ordering. Also, the refinement residuals or the judgment factor are quite high, which basically means that this symmetry is no longer correct to describe the structure that you have. You should go to a lower symmetry. This is by nature. And what about the crystals that don't have three-dimensional charge order, only diffuse scattering? I also tried to refine it, but the same story holds here. We have elongation of the lutetium, and then therefore it was splitted, and means that the structure is not anymore the hexagonal one. Okay, that means I need to check the lower symmetry space groups. This is what I did, but this what you see here is the table, summarize all the space group that has lower symmetry I tried. Of course, neglecting the superstructure reflections for the commensurate charge order type. And the upper part can show you that this one, the orthorhombic CM-CM, has the lowest residuals or judgment parameters or factors, which basically means that every single space group that contains threefold rotation is broken. Threefold rotation is not there anymore. However, for lower symmetry, these here in the lower part of the table, I can tell you that this one is not correct because the values are high. What about the rest? Unfortunately, there is no really clear preference to decide what is the correct one. And this is due to the complex structure. The last thing we did is the X-ray magnetic circular dichroism, what we call XMCD. It's just the use of circularly polarized X-ray that is left circularly polarized and right circularly polarized in the application of magnetic field. And then one can take the difference between these two absorption cases and get what we call the XMCD signal that you see here. What I want to tell you, of course, this was done at the synchrotron PC at the high field diffractometer. The main message to take here, if I compare it with the 124, you have two peaks. I mean, this is the reason why we do the XMCD. We want to resolve the valences of the iron +2 and +3. Yeah, so we have these two peaks, upper one, Fe +3, and the lower one is Fe +2. So, what does this mean? That means in the lutetium ferrite, if you see this red one, that it's opposite to what actually in the structure. So, the positive peak here means that you have a net moment that is in the negative direction. And what about the Fe +2? Also opposite to what you see here. So the negative peaks means that you have iron valences of the +2 opposite in this direct in this direction. Okay, and now if you came to the 237 and 3410, you see that also we have reduced magnetic correlations, but still we have the same spin structure in the bilayers as we see in the 124, because you have the same Fe +2 here, but however the Fe +3 you have a reduced peak. What does this mean? That means we have more negative +3, more positive +3 in the compound. That comes from the single layers. Okay, I hope I was able to give you some information about my work. So I have showed you that I was able to grow crystals of 237, but also we get 3410 that are stoichiometric enough to exhibit superstructure reflections, meaning long-range charge order. But also that the correlation length in the 3410, the largest. And also we have reduced magnetic correlations in comparison to the non-intercalated compounds. And according to the symmetry analysis, it just shows you that for 237 you have two possibilities, either polar or antipolar one, while for the 3410 it's definitely polar, according to the symmetry analysis. As an outlook, this still needs to be confirmation based on X-ray diffraction for a better quality samples. Yeah, for this I would like to thank Brain Game for funding 1 year of my PhD, and my colleagues, my supervisor, and other people from different institutes. Yeah, thank you for your attention.